So warm up 74 for today. Let me give you a code. Give me a second. All right, warm up 74 is on your screen. Let's get started, please. That shouldn't take you long. Copy and go. All right, let's see. Get us started, please. With the sum. The sum. What'd you get for the sum? Noel, sum. I'm sorry? Number 1. Okay. Jaden, what'd you get for the sum? Plus 2i, that is correct. Pass someone for the difference. Negative 8 plus 8i, that is correct. Product or multiplication, pass someone. $54i minus what? Let's see. Said negative 90 plus 54i. 90 plus 54i. Okay, let's double check. 7 times 15, that's 105. 7 times negative 3i, negative 21i. 5i times 15, that's 75i. And 5i times negative 3i, that's negative 15i squared. Okay, so if you combine the i's, 75 minus 21, that is 54. Okay, so far so good. 105, however, the negative 15 and multiplies I squared, which is what, everyone? Negative 1, yeah, so negative 15 and negative times negative 1 is positive 15, so the 90 should be 120, 120. Double check that, please. 120 plus 54i. All right. Number 2, you set it equal to 0, and this one you can actually solve by factoring. Bless you. We got negative 12 and negative 4. Factors of negative 12 that add up to negative 4. Pass on one. Factors of negative 12 that add up to negative 4, negative 6, and positive 2. So my factors are x minus 6, x plus 2, all that equal to 0. And then to solve, we just set each one equal to 0, x minus 6 equal to 0, x plus 2 equal to 0, so x equals 6, x equals negative 2. Hands if you got that by yourself? Yeah, some of us? Okay, good. Number 3. Number 3, if I was to graph this, let me graph it down here. F of x is going through the point of origin like so, at 0, 0. So, once we do the write our new rule with all these parameters, what is our new vertex? Tell your neighbor the new vertex. New vertex. Pass someone, Alyssa. Christina, new vertex. Negative 4 and 5, that is correct. Or H, negative 4, and K, 5. So negative 4 is over here, 5 is up here. So my new vertex is going to be somewhere up there for g of x. And last but not least, solution for the system with substitution. Pass someone, Christina. Jessica, what'd you get for the solution to that system? -3, -3. Hands, have you got -3 and -3? That is correct. Let's check. If x is -3 and we substitute it in here, this is 3 minus 6. Yes, -3. All right. Thank you. All right. Send me your notes for the warm-up, please. All right, so the agenda for today, warm-up number 74, complex numbers. And tonight's home play, pages 135 and 136 only. After you copy the agenda, go to Canvas under the quadratic equations module. Turn in last night's home play. Hopefully it was plenty of practice for addition, subtraction, multiplication of complex numbers. Yes? Yes, that's a cue. We love it. All right, good. All right. So once again, last night's was page 133, 134, and tonight 135, 136. And once you do that, get a Cornell note ready so we can get started. I'll give you some time. All right, here we go. Our objective for today, I can define and compute complex numbers. I can define and compute complex numbers. What's our main concept for today? Still, complex numbers. So turn to your neighbor, let me know the definition for complex numbers, please. All right, good conversation. So on your screen, type in your definition for complex numbers and one example. 30 seconds. Go. All right, correct answer on your screen, one real number and one imaginary number. And the example given is 3 plus 9i. All right, yeah, I'll go with that. All right, thank you. So, yesterday we covered just identifying which one was which. We're good with that. From there we got into computation, which is sum, difference, and product. That was last night's home plate. And then from there we got to electric circuits. I presented a basic one. From there I showed you more intricate ones. And then I gave you a table where you copied the different components that we're going to be looking at, which was the resistor, inductor, and capacitor. And we said that from this point forward that in order to shorthand it on our circuits, we're just going to use the letter R for resistor, I for inductor, and C for capacitor. So far so good, yes? Yes, yes, thank you. All right, and then I gave you guys this circuit. So before I move on, tell your neighbor which one is the inductor. Tell your neighbor which one's the inductor. All right, Ivan, which one's the inductor? Yeah, the one on the right, inductor. All right, which one's the capacitor? Tell your neighbor the capacitor. All right, capacitor, Delilah, which one? The bottom one, yes, so this is our C, which means this is our resistor. Okay, so with that said, let's see how you do with this one. Don't copy it on your paper, but I want you to label your screen. You got 30 seconds. Label each component, please. Go. Correct answer on your screen, capacitor, capacitor, resistor, resistor, and in the center, inductor. All right, I think we got this. Let's do another one. Label your that circuit on your screen, please. 30 seconds. All right, looks like everybody got it. So, once again, correct answer on your screen. Resistor, capacitor, resistor, inductor. All right. So, and one last one. Don't label it on your screen. Just tell your neighbor what each component is. All right. All right, thank you guys. Very good, very good. All right, so write your utensils down, look up to the screen. I'm going to go ahead and give you a quick intro to electronics. All right, here it goes. You don't have to copy anything. So for those of you going into the, some of you that are going to become foremen or working with the electrical lines or going into technical fields such as electronics, this is the basics. So here we go. Electric circuits work on electric current, which means electricity. Now, the types of electricity that we have are two types. AC, which means it's those outlets that you have on the wall, and DC, which is all batteries. Direct current is all batteries. That's why the batteries have a plus and a minus, or a positive and a negative. Alternating current is on the wall, and I don't know if you notice from time to time when you plug in your charger for your phone, you don't even worry about which direction you plug it in. Why? Because it's alternating current. You're like, what? Right? All right. Now, all that current is measured as to how much current can go through a particular component by something that we call impedance. Now, the easy way that I can put that is if I was to show you the entrance door here to my classroom, room 106, and if you look at it, the frame of that door, how many people do you think can get in at once? Think about it. How many people will fit going into that door, only one at once together? At most, what, like 5 people? Like if they're back to back, skinny people, like just squished in. But that's the most it can go. Well, that is what we call impedance. How much can flow through a certain part. So that is measured by this symbol. This symbol is a Greek symbol to the letter omega in Greek. And they use the letter omega because it's ohm. That's what we call the impedance that we're going to use. Okay? So that's a quick intro. Now check this out. Yesterday, I gave you guys a table that had the component, the diagram used for the component, but today we're going to add values to that. So mathematicians and scientists figured, well, we can add a value to the resistor by making its value, or the resistance of the impedance going through that component, a real number. For the inductor, it's going to be an imaginary number where B is greater than 0. And for the capacitor, it's going to be an imaginary number, but B is less than 0. Now, some of you are still wondering right now, what does that mean, Mr. Q? Well, I'm going to put it in simple terms, so I want you to copy this table again, but now leave the right side blank so I can put it in simple words. So the top of the left column reads circuit component, and you write resistor, inductor, capacitor. The middle column says symbol in circuit diagram. They give us a symbol for each. In the last column, it says we're going to represent that using a complex number. So, in simple words, a resistor becomes a constant, in parentheses, basically a number without a variable. An inductor becomes a positive imaginary number, and a capacitor becomes a negative imaginary number. So, let's see. Let's put some examples underneath that explanation. So the resistor, we use the letter R to label our diagram. That's the symbol that we are looking for. And we can translate that into a constant. So think about any constant. All right? I'm going to think I wonder what number I'm going to pick. What number shall I pick? Okay, 23, Michael Jordan. That's a constant. Why? Because it does not have a variable. All right, so if we go to the inductor, we use the letter I for shorthand, and that's the symbol. So that becomes an imaginary number. So think about a positive imaginary number. Any positive imaginary number, I'll just say, I don't know, 3i. Is 3i a positive imaginary number? Yes. So with a capacitor, we're going to be using the letter C for shorthand. That's the symbol. And think about a negative imaginary number. All right? Share with your neighbor a negative imaginary number so they can write it in there. All right? Frida, give us one. Negative 2i. Yes, that's a negative imaginary number. So from now on, when we see a circuit, and if they give us the impedance or how much current is going to flow through the component, we're going to translate that to either a constant, a positive imaginary, or a negative imaginary. All right? So, we good? Copy this circuit, please. The circuit to the right, and underneath that circuit, I want you to copy that table at the bottom, like so. And we're going to go through the process to make sure we got this. So I'll give you some time to copy the circuit and the table. We'll get started. All right. So as you're finishing copying that, before we get started with anything, label the resistor on the component really quick with an R so that you know which one it is. All right. Show your neighbor, please, to make sure they got it. Which is the resistor? All right. So, which is the resistor, Dylan? The top one, so I'm going to label that with an R. There it is. All right, and they give us the impedance. The impedance is 4 ohm. But what did we say that was going to be translated into? A constant, so that would be 4. Fill that in. Next, let's go to the inductor. Tell your neighbor the inductor, please. Which one's the inductor? All right. Alex, the inductor, which one's that? The what? The right. So I'm going to label that I. And the impedance on that one is 3 ohms. So that, we said, turns into a what? A positive imaginary. So that would be 3I. All right. So last but not least, the last one over here should be our capacitor, and the impedance is 5 ohm. Tell your neighbor what you're going to write right there for the capacitor. All right, Juan, what are we going to write in there? I'm sorry? Close. Anaya, help him out. Negative 5I. Remember, capacitor will always be a negative imaginary. Make a note. All right? How are we doing? Good? Yes? All right. So, now that we know how to identify on our circuit which one is which, and then from there go and fill in our table over here as we did here, let's do one completely. You don't have to copy this next one. Do it on the screen, please. Fill it in on the screen. 20 seconds. Go. Let's see how we did. Looks like we got it. So correct answer is on your screen. The resistor is just 9. Inductor is 7I. And the capacitor is negative 10I. Hands if you got that. All right, I think we got it, right? Yes, Mr. Q. All right, good. So let's do another one. There it is on your screen. Fill that in, please. Give some time. Go. All right, correct answer on your screen. Hands, have you got that? All right, so if you notice, we're following the process. First, we label our circuit with the initial so that we know where it's located. Then from there, we translate that into either a real number or an imaginary number or a negative number. Now, these are simple because they're simple circuits. So what if I crank that up a notch? Let's see. I'm going to challenge you. See how you do with that one. Let's see what you get for that. Fill that in, please. Before you do, I want you to look for the resistor and tell your neighbor what you're going to write in the table. Talk it with your neighbor. What are you going to write in the table for resistor? Then fill in the entire table. Go. All right, I think we got it. Here goes the correct answer on your screen. All right, tell your neighbor how they got that answer, please, for each one of those. Talk it over to your neighbor. How did they get those numbers, please? Yeah, so basically, if you notice the resistor, there were two of them, 4 ohm and 5 ohm, and all they did, they combined them to give us 9. And then the inductor was only 1, which was 7. That was a positive 7I. And then the capacitors, there's 2 of them, 1 2 ohm, 1 3 ohm. Combine those, that gives us negative 5I. All right? So from 1 to 5, how comfortable are you with labeling and translating that into numbers? All right. Yeah, we got this. Okay. So with that said, copy this formula, please. This formula is the formula that they came up with in order to find the voltage going through a component of any circuit. And V stands for voltage. The current is the letter I, and that one is in amps. And this current, they usually give us as a complex number, and it's going to look like a binomial, but remember, a real number plus an imaginary number. That's what a complex is going to look like. The impedance, if you can recall, we've been working with that so far up to right now on our table. That's the numbers that we came up with. We have our resistor, inductor, capacitor, and then we come up with these numbers. That's the impedance. And remember, the impedance is measured in ohms. Okay? So, now that we have that, I'm going to give you a circuit. You're going to copy the circuit either underneath that or to the right, and also copy the table. For the table that I give you, I want you to, for every row, I want you to skip 2 lines so you can have plenty of space to do work, because we're going to start getting into some work with this. All right, here's the circuit. Copy that, the circuit, and then copy the table underneath that. And remember, for each row, it's about 2 lines. All right? Copy that. I'll give you some time. All right, here we go. So, y'all ready? So first things first, let's label our circuit with all the initials of each component. So, help me out. Which is the resistor? Fredo, resistor. So R. How about the inductor? 3. And of course our capacitor is down here. So now that we know what each one of those is, let's fill in our impedance, translating that into numbers. So, write that in there on your table. And help us with that column. Jaden, go. What do I write for the resistor? 4. Inductor? 3I. Capacitor? Negative 5I. All right. So far, so good. Next. Writing utensils down, look up to the screen. Now, this is what I'm going to do. I'm going to do just one of them, and you're going to find out that it's fairly simple to follow from there. So look to your screen. So here I'm going to write my formula, and the formula reads V equals I for current. And what is the current that they give us? The current they give us is that. That's the I. And then we're going to multiply that times the impedance. So don't copy yet, just pay attention. My goodness. Here it goes. V equals, instead of the letter I or variable I, I'm going to substitute in there what? 24 plus 12I. There it is. What is the impedance for the resistor? The impedance for the resistor is 4. So now that I have that, now we get to work. Here we go. Distribute the 4 into the both terms in the parentheses. 4 times 24, that is 96. And 4 times 12I, that is 48I. And it's a positive, and that's the voltage that can go through the resistor. Copy that. And I'll give you a head start so you can finish up with the inductor and the capacitor the same way. And go. All right. Check with a neighbor, see what they got for the inductor, or see where they're at, and then I'll get Diego Rosas to help me. All right, so let me just write it out. Our current is 24 plus 12I. And we're going to multiply now times what? 3I. Okay. So, Diego Rosas, help me out. 3I times 24. 72I. Okay. Next, 3I times 12I. 36I squared. Am I done? The I squared turns into negative 1, so if you multiply that times 36, that gives us negative 36, and then at the end we write what? Plus 72I. That is correct. Let's go. Let's go. All right, so double check your work on the capacitor to make sure that's what you did at the end. Don't forget to substitute for the I squared a negative 1. And then you simplify that. And the last one, we're going to multiply the current times negative 5I. All right. Finish that, and then I'll have somebody give us just the answer for that one. All right, check with the neighbor, see what they got. What is the voltage going through the capacitor? All right. Diego, pass someone. Valente, what'd you get? What? Oh, 60. minus 120I. Hands, have you got that? That is correct. Let's go. Make sure at the end you substitute for -1 on the I squared, all right? Send me your notes, see what you did. I want to see your notes. Problem number 6Q, the current that they give us is 18 plus 6I, and you copy that electric circuit and fill in the table, find me the impedance, and find how much voltage going through each component. Copy and go. I'm going to forward the screen so that as soon as you're done, you take a picture, submit that. And that's going to be our last problem. I'll stop the video at this point. And once again, make sure you do your home plate for the practice, because tomorrow, let's go, let's go. Yeah, and it's also assembly schedule. Let's go, let's time. Yeah. Yeah. What's that? Yes. All right.